Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will carry out a residual analysis for a small dataset. Our analysis will be based on plots of raw residuals, but at the end we will make some comments about other options. Our main objective will be assessing the assumptions of regression models using these residual plots. Okay? Well, let me show you something that I prepared for you. This is the example that we're going to use, the small data set that we're going to analyze using a residual analysis. Okay? So, if you take a look at what we want to do here is we would like to see if there's a relationship between store size and annual sales. Okay? And we have a small sample of 14 stores to study this relationship. Okay? And as you can imagine, the idea would be trying to predict sales from store size. On the next slide, we have a table that contains that information from that small sample of 14 stores. Okay, as I said, size will be our predictor variable, and y, annual sales, will be our response variable. Okay, so as you can imagine, we will use R to carry out this residual analysis. Our first step, as usual, will be entering that information. In this case, since we have a small data set, we will do it using that C function, concatenate. So 1.7, 1.6, 2.8, 5.6, 1.3, 2.2, 1.3, then we have 1.1, 3.2, 1.5, 5.2, 4.6, 5.8, and 3. Okay, y we have 3.7, oops, sorry, 3.7, 3.9, 6.7, 9.5, 3.4, 5.6, 3.7, 2.7, 5.5, 2.9, 10.7, 7.6, 11.8, and 4.1. Okay, so as you already know, it's always a good idea to plot your data first, right? So let's do that. Let's make a scatter plot of our data set. You have used that function before, plot, to make a scatter plot. Let me use solid circles for that scatter plot. I like blue, so these circles will be blue, and yeah, that's it. Okay. So it seems, right, according to that scatter plot, that we have, roughly a linear relationship between x and y the association seems to be positive. As x increases, y increases. The strength of the relationship is kind of strong. If we want to provide a numerical measure of the strength of that linear relationship, we know that we could compute r, the correlation coefficient, and the closer r is to 1, then the stronger the relationship, the linear relationship. Okay. So how about we find the least squares regression line? So let's use that LM function that we have been using a lot lately. We know that the syntax is first we want the response, then the predictor variable. So how about we make that scatter plot? But now we will include the least squares regression line. Okay, so we know that with the command AB line, we're going to be able to include that on our scatter plot on the same graph, and AB line needs as the information the y-intercept and the slope, and that's exactly what we're going to be getting with that coefficient. We're going to be getting the coefficients of the least squares regression line. Now let me just tell R that I want a dashed line with that LTY. I will tell R that I want a dashed line, and I want that line to be red. Okay, so there we are. Okay, so we have summarized that relationship using the least squares regression line. And now let me remind you, when we have one of these simple linear regression models, we have assumptions about the fluctuations, those random fluctuations, the errors, the epsilons. The assumptions are that those errors are independent, that they are normally distributed, and that they have the same variance. They have a common sigma square, remember? And of course, the first assumption is that something like this, something like that dashed red line, is going to be a good approximation to the relationship between x and y, meaning what we are assuming is that the association between predictor and response variable is roughly linear. So if we summarize those four assumptions, we have linearity, independence, normality, and variance constant. Okay, so if you want to remember those, you could use an acronym, right? LINE: linearity, independence, normality, and variance, constant variance. Okay, or equal variance, right? Okay, so the first assumption, the linearity, right? A first approach is making a scatter plot like we just did, right? But we will see that residual plots can also be used. They can also be helpful to assess linearity. Okay? Okay, so the second assumption, right, the independence of the errors, again, we can make a graph of the residuals against the time at which the observation was recorded, and if we saw a pattern there, we could, maybe put into question the idea that the observations are independent, right? Okay, again, we're going to be making a residual plot and checking whether or not the independence assumption is a reasonable assumption. Okay, about the third assumption, the normality assumption, right? Why is this important? So at this point we know that it is important from a theoretical perspective, because using that assumption, right, that the errors are normal, we have seen that that distributional assumption for the errors has consequences for our estimators for beta 1 hat, for beta 0 hat, and we have used those distributional assumptions for beta 1 hat, for instance, right, the estimator of the slope, to come up with confidence intervals, prediction intervals, hypothesis tests, right? So that's why that normality assumption is so important. Okay. However, tests like the f-test we know are robust to the normality assumption, meaning that, well, if the normality doesn't exactly hold, the conclusions will not be extremely affected. Okay. Anyway, but it's important to check if the normality assumption is absolutely unreasonable. Maybe we should try and find something else, right? Okay, so the fourth assumption, the equal variance, right, the constant variance assumption, for that one, well, again, remember that we are assuming that the distribution of the epsilons is normal with mean 0 and a common variance sigma square, right? So if that assumption doesn't hold, it will have an effect on our inferences about the parameters of our model beta 0 and beta 1. In some cases, right, if that assumption, if the equal variance, constant variance assumption doesn't hold, well, sometimes one way of fixing that would be transforming our data. Another option is one called weighted least squares. Okay, so now let's talk about how we can use our graphs to evaluate those assumptions, right? First one, the one about linearity. As we said, well, our first attempt would be making that scatter plot, but we also mentioned that we could use a residual plot to assess the assumption of linearity. Okay, so the way that we're going to be doing that using a residual plot would be on the vertical axis we will have the residuals, and on the horizontal axis we will have values of our predictor. Okay, so let's try and do that. Let's try to assess linearity with a residual plot. So we already have our data here, x and y. Okay, we already have our model, our linear model. It's a classical regression model. Okay, and we know that there's a way of quickly finding our residuals, right? Using the function residuals and the name of the model that we're going to be using to compute those residuals. So that would give us the 14 observations, well, the 14 residuals corresponding to our 14 observations. Okay, so let me save those residuals in an object called E. Remember that we use the letter E to refer to the residuals, which are the basically the quantities that we're going to be using to estimate the errors, right? The unobserved errors. Okay. So now, as we said, if we're going to be using residuals to assess linearity, one of the assumptions, what you do is on the horizontal you graph your predictor variable, on the vertical your residuals, and as usual let me use solid circles. I like solid circles. I like the color blue. And if you want to add a main title, you could do so with the function main. How about predictor variable against residuals, or in this case it would be size against residuals. Okay, let's see. There we are. Okay. Now, how about, because we know that you know the errors have a mean of 0, right? How about we add a horizontal line at 0? And to do so, all we have to do is use again that AB line command, but if you want to add a horizontal line, use an H, and at the level where you want to place that horizontal line, in this case 0, LTY we have used before, that's a dashed line, and again I want that line to be red. Okay. Make sense? So what you're looking for here is you don't want to see any kind of pattern, any kind of relationship between X and your residuals. If there was a clear pattern, a clear relationship between your predictor and your residuals, that means that the linear model is not suitable, right? That the linearity assumption is to be put into question. Okay? Okay. So from this, right, we can see that, yeah, there's some variation, right? But we don't see a pattern, and then, you know, the linearity assumption seems to be reasonable. Okay? So again, what you want to see here is basically no pattern, okay? Something random fluctuations around 0. Okay? Okay. So, next assumption, the assumption of independence. As we said, the thing is, if you make a plot of your residuals against the time at which your observations were collected and you saw a pattern, for instance, a cycle, right? Then that means that the observations are not independent, and then the errors will not be independent. Okay, so then the independence assumption is not reasonable. So in this case, all these observations were taken at the same time, so we're not going to be worrying about that. Okay. Next assumption, the normality assumption. So we have already established that it's important for inferential purposes, right? So we can compute our confidence intervals, our prediction intervals, carry out our hypothesis tests, right? Okay. So you also remember that in another video we talked about QQ plots, right? And that's a graphical way of assessing normality. Let's use those guys, QQ plots. to assess the normality of our residuals. Okay, so we already have our residuals here, right? Let me remind you that the function that is going to help you, the built-in function in R that is going to help you make a QQ plot is QQnorm. All you need to do is the name, enter the observations that you have. In this case, we want to assess the normality of these guys, the residuals, and that's it, right? So again, let me use solid circles, same color, blue, and we know that what we would like to see here is these points being close to forming a line. Okay, now let's add that reference line, the QQ line. Let me make it dashed, and again I want that line to be red. Okay, now let me remind you also that at the end of that video, when we talked about QQ plots, we saw that for small samples, even right when normality holds exactly, remember, if I remember correctly, at the end of that video we generated 30 observations coming from a normal, standard normal, and then we made the corresponding QQ plot, and we saw some deviations, right, for a sample of size 30, and when the normal assumption held exactly, right? So in this case we have a sample of size 14. So except for maybe this guy here, we're seeing some deviations, right? Well, that kind of deviates. These guys are not that far from the line, right? So it seems that we don't have to be overly concerned, right? And again, it's difficult to assess normality when you have a very small sample size. So unless you see something, unless you see a flagrant violation of the normality, then okay, seems reasonable. Remember that we also, at the end of that video when we discussed QQ plots, I showed you what happened when you did this, but for a sample of exponential, well, of numbers coming from an exponential distribution. Then in that case, clearly that was not anywhere close to that line, right? Okay. So in this case, okay, given that we have a small sample size, it seems that it is reasonable to assume that they have a normal behavior. Okay. So the other assumption, the assumption of equal variance. As we said, and let me go back to that, right? As we said, one way of assessing if yeah, that's good. One way of assessing if the variance is roughly constant would be just you know, seeing that plot of the residuals against the predictor, right? And seeing if we are not seeing something like this, like funnel shape behavior. So meaning that, as for instance, if we saw that as x increases, the variability increases, that would be problematic. Or the other way around, that you have that the variability is very big here, and then as x increases, that variability decreases, right? That would tell you that the variance the assumption that the variance is constant is not reasonable, right? But in this case, we seem to have a, a constant variance. Okay. Now, there's another way of graphically assessing if the equal variance assumption holds, approximately. First, bear in mind here that in this case, yeah, we have only one predictor, but in the near future we would like to extend what we know for the simple linear regression for more than one predictor, multiple predictors. And if that was the case, doing something like this, maybe it isn't such a good idea. So another way of assessing the equal variance assumption is plotting the residuals against the predicted values of y. So meaning residuals against y hat. Okay, so let's do that. Okay, so we know that one way of getting the predictions is just using, let me remind you that if you type this, names of, we call that guy model, I believe, yeah, mod. So you have a bunch of things, among them the residuals, but you have also the fitted values, meaning your predictions, your y hats. So let me create an object called y hat, and it's going to be the fitted values for that model. And if we type this, just fit r, we'll understand that that's what we want. We should have just 14 numbers. Okay, so that's what we have, our 14 predictions corresponding to our 14 observations. Okay, so what we're going to be doing next is, instead of using on the horizontal the predictor variable, we're going to be using y hat against residuals. Again, solid circles, I like those. I like the color blue. And how about we add a main title that reads, I don't know, predictive values against residuals. Just like last time, how about we add a horizontal line at 0 there. Okay, so just another way of assessing that fourth assumption, the equal variance assumption. Okay, so let's summarize what we did here in this video, you and I together. What we did is we used residual plots to assess the 4 assumptions in a linear regression model. And we said that we could use the acronym LINE to remember what those 4 assumptions are. L for linearity, right? So to assess that, well, the first step would be making a scatter plot, right? The other one would be doing what we did at first, right? Making a graph of the residuals against the predictor variable, right? And see if we had a random pattern, right? We didn't want to see a pattern in that case, because if we saw a pattern in that case, that would be something that we should be concerned about. It would mean that the linear model is not a good idea. Okay, so that's the first one, right? The second one, independence. What we said is that if we have the time at which the observations were collected, it would be a good idea to make a plot of time against the residuals. And then if we saw a pattern, for instance a cycle for those residuals, right, then that would make the independence of the errors not very reasonable, right? Okay, so that's as far as independence goes. Then the normality. To assess the normality of the errors, what we did is we used QQ plots. Okay, and we know that that assumption is important because that distributional assumption for the errors has consequences for our inferential procedures, such as confidence intervals, prediction intervals, hypothesis tests. And finally, the equal variance assumption. Now we know that we have two routes, two possibilities as far as graphs go to check, to assess that assumption. A graph of the residuals against the predictor variable x, or a graph of the residuals against the predicted values y. Okay, and what we said is that this will be a good choice when we generalize what we're doing, when we go from one predictor to several predictors. This would be a better idea to check the equal variance assumption. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.